Hello and welcome to Week 2 of G147, Geology of the National Parks. This is Topic 1, our first lecture for the week, and we will be covering decompression melting, mantle upwelling, and basaltic volcanism. These first two items are basically the processes by which we create magma and feed basaltic volcanoes. So let's get into it. Just to recap, remember that the interior of the Earth is made of a few different layers, which can be defined either by their chemical composition, I got my laser pointer, either by their chemical composition or by their physical or mechanical properties. The mantle is made up of ultramafic rocks. That is rocks that are comparatively low in silica, less than 50%, less silica than mafic rocks, that is, more magnesium, more calcium, and more iron than mafic rocks have. The general composition of igneous rocks goes ultramafic with the least silica, mafic, intermediate, and felsic with the most silica. Also remember that our matter that everything is made of has different phases, solid, liquid, and gas. On Earth, generally our minerals are either solid or liquid. They're only liquid when they're molten in magma, and they're solid all the rest of the time. The boundaries between phases are called phase boundaries. And when you cross these boundaries is how you go from one phase, i.e. solid, to another, i.e. liquid. In this lower phase diagram, we have the phase diagram of ice, and where this big arrow goes, it goes from very, very high pressure to lower pressure, and in doing so, it crosses the phase boundary from solid to liquid. Speaking of water, water is a pure substance made up only of H2O, dihydrogen monoxide, but rocks are much more complicated. They are composed of many minerals, each of which is a separate substance. For example, granite is made up of quartz, feldspar, and mica. The minerals are unique chemicals, and the rock is made up of lots of different minerals. Each mineral has its own melting temperature. That's important to remember. Especially here, this is called Bowen's reaction series. This is the series of processes that govern what minerals melt where, in what conditions, and how your magma will evolve over time as its conditions change. We start with ultramafic rock from the mantle, for example, and it is made mostly of three minerals: olivine, pyroxene, and calcium-rich feldspar. These are all comparatively silica-poor minerals. And the lower in this chart you go, which also shows cooling magma, you get higher silica rocks as you go down. All the way quartz at the bottom is 100% silica. We will talk more in detail about this as this course goes on. Also recall the geothermal gradient called the geotherm, which is the temperature at depth in the Earth. It's hotter when you get deeper, and you can get melting of these mantle rocks due to changes in either temperature or pressure or both. All of the mantle is solid, and it is closest to melting at the asthenosphere. And remember, it is solid, it is a plastic solid, and it is not molten, but it is very, very close to melting within the asthenosphere. How does the planet cool? We're not really sure. There's a couple of different models, one where the mantle is divided into upper mantle and lower mantle, which convect separately and do not mix. And there's another model where you have the whole mantle convecting and mixing over time. Hot spots are an example of whole mantle convection, where we think most of the melt comes from the core mantle boundary and rises up through the whole thing to feed hotspot volcanoes such as Hawaii or Yellowstone. But we'll talk about that more in detail later on in this lecture. But regardless of what model of mantle convection you use, there are places that on the Earth where plastic solid mantle is upwelling, moving upward toward the surface. And in these places, your rocks are moving from very high pressure down inside the Earth to comparatively quite low pressure without cooling very much. Places where we have upwelling mantle rock include divergent plate boundaries, like a mid-ocean ridge. Here we have upwelling mantle rock. This box here must rise because it's upwelling. And as it does so, it melts partially. It begins to melt. Some minerals are melting and feeding volcanism at that mid-ocean ridge. The other places include thinning crust or lithosphere, such as a rift valley where a continent is stretching apart, like in the East African Rift Zone. As the crust thins, your asthenospheric mantle will rise and begin to partially melt, feeding volcanoes within that rift system. And the third place is an upwelling mantle plume, also called a hotspot, where you have rocks from deep within the mantle rising up without cooling, and this causes the pressure to drop and the temperature to remain the same. This can create a lot of melt and can feed quite large volcanoes in a hotspot volcano setting, such as Hawaii or Yellowstone. This is called decompression melting, when hot rock moves rapidly enough to lower pressure that it doesn't have a chance to cool. When it reaches the phase boundary, also called the solidus or liquidus, when it reaches that phase boundary, which is a combination of temperature and pressure, it begins to melt. But rock isn't like water. The minerals don't all melt at the same time. You get partial melting. And partial melting is a very important concept in igneous rocks, in volcanism, and in how our Earth does chemistry. This little experiment shows really well how partial melting works. So in A, we have a mixture of white wax, just paraffin wax, green glass, black plastic, and this silver aluminum wire. They heated this mixture for 30 minutes at 50 degrees Celsius, and the wax all melted. So now we have a partially molten mixture where we have liquid wax, and then solid plastic, solid glass, and solid aluminum. They then heated this further to 120 degrees Celsius for 60 minutes, and most of the plastic has melted as well. So now we have a mixture of three components. We have melt, we have aluminum wire, and we have green glass. If you extract this melt, this molten mixture of wax and plastic, you get a substance of a different composition than the original whole composition. If you took all of this, ground it up into a powder, and took that whole composition, it is now changed once you extract just the molten plastic and wax. So you have a different overall composition in D than you did in A. This is basically how magma chambers work. How you go from a no-melt situation where you have just solid rocks, and then as your, for example, temperature increases or your pressure decreases, as we've discussed, you get more and more melt. And you also get more and more relative silica content will drop as you have more things melted. So you have the most silica in your igneous rocks at the lowest temperatures, and the least silica in your rocks at the highest temperatures. In this figure, we have pressure with depth and temperature increasing to the right. So we have solid on the left, and your dark line, your heavy line, is the normal geothermal gradient. But then if you decrease your pressure, your geothermal gradient changes, and this dashed line shows your geothermal gradient once you've upwelled your chunk of solid mantle. And that puts you into this zone of a mixture of liquid and crystals called partial melt. It's very rare for a chunk of mantle rock to completely melt and give you 100% liquid. So most of our magma chambers and most of our volcanic systems stay within this liquid and crystals partial melt stage. Decompression melting is due to upwelling mantle rock. It affects the local geothermal gradient, and you get partial melting of that upwelled rock. The magma created is richer in silica than the ultramafic mantle. That's important. And you get mafic magma from this, and it forms a volcanic rock called basalt. This is important. You get basaltic volcanoes at divergent boundaries for the most part, and other areas of rifting or crustal thinning, such as the American Basin and Range, which we'll talk about shortly, as well as at hotspots and areas where you have mantle plumes rising. That's these two situations here in the middle, mid-ocean ridge and hotspot, where you have, at a mid-ocean ridge, you have high temperature rocks that have upwelled and passed the solidus, the zone where you begin to get partial melt. And at hot spots, you have very hot rock that has greatly reduced its pressure and increased in temperature, so you get you begin to cross that solidus at a slightly deeper zone, generally the base of the lithosphere. When continents break apart at divergent boundaries, new ocean basins are created, and this involves a large amount of volcanism, and new ocean crust is created at that divergent boundary. The new ocean crust that gets created is mafic in composition. This is a review. Divergent plate boundaries are complex systems. There's really only one in the world that is active and can be easily studied, easily understood, and that is the Eastern African Rift Zone. Oftentimes, a new divergent boundary will begin as an upwelling mantle plume, where you have rising mantle material causing the crust to break apart, oftentimes in sort of three legs, three branches. These rising convection currents create a spherical bulge. If I go back, you can see that bulge in the first stage of this diagram, where your crust is warped, stretched, and domed upward. And your crust breaks in three places, creating what's called a triple junction, just a place where three tectonic plates meet. We see this today in Arabia and East Africa. The Arabian plate has separated from the African plate, giving us the Red Sea and the Gulf of Aden, and the African Rift Zone systems have begun to crack down the sort of eastern flank of the African continent. In these rift zones, we have tons of volcanoes, including Erta Ale, which has one of the world's few lava lakes on it, Oldoinio Lengai, which has a very interesting chemistry, where it is very primitive. Basically, molten mantle rock is erupting there at Oldoinio Lengai. And we also have Kilimanjaro down here further in the south, the tallest, one of the tallest volcanoes in the world. As these cracks propagate away from the triple junction, your lithosphere breaks, the crust breaks, and the lithosphere breaks, creating these rift valleys, also called a graben. A graben is a linear valley bounded by faults where you get crustal thinning or stretching. The center of your rift valley marks the plate boundary, and the two plates on either side are diverging or moving away from each other. The hot rock from the asthenosphere rises to fill that zone of thinning and stretching and melts by decomposition, producing mafic magma and feeding volcanoes along your rift valley. The repetition of this process eventually creates a new ocean floor. There's also a thing called an olicogen, which is a failed rift. One of those is in the central United States with a bunch of national parks in it. This is called the Mid-Continent Rift, and it represents a time where North America tried to split apart from the middle, but ultimately failed. And we have a great thick stack of mafic rocks running through the center of the North American continent here. Once an ocean basin forms, the top of your mid-ocean ridge is at the plate boundary. And there's a small sort of graben summit valley along the length of that rift zone, and that's your plate boundary. The mantle part of the lithosphere differs from the asthenosphere only in being colder and more rigid. At the mantle rocks are hot, or at the ridge, the mantle rocks are really hot. And the lithosphere is almost entirely just your oceanic crust. So your lithosphere and your oceanic crust are very, very thin, almost zero thickness here at your oceanic ridge. As the plate moves away from the ridge, the mantle cools and becomes brittle and becomes part of the lithosphere. As you move away from your mid-ocean ridge, the lithosphere is now thicker and denser and sinks down into the asthenosphere by isostatic equilibrium. So let's move on to areas where you have thinning crust or lithosphere, a continental rift valley. This could be a start of a new divergent plate boundary, or it could be different. This is your East Africa Rift Zone, as we already discussed, where you have an active continental rift, where the continent is breaking apart. Frequent volcanoes, lots of volcanoes in relatively low altitudes. In the United States, we have a thing called the Basin and Range and the Rio Grande Rift. This is an area of continental rifting, sort of, but it's not a plate boundary. The underlying forces behind the basin and range are not entirely understood, but this region has stretched. Northern California, Southern Oregon has stretched westward relative to the Rocky Mountains, and this crust has now thinned and pulled apart, giving us long series of mountain ranges and long valleys. Thus, basin, valley, and range mountains. There's a ton of national parks in the basin and range, and we have actually active volcanoes and lots of earthquakes all around the perimeter of the basin and range area. There is most of the active stretching in the basin and range today occurs along its perimeters here in Eastern California, called the Eastern California Shear Zone or the Walker Lane, and then here in Utah, which is the not the Walker Lane, this is the Wasatch Front, where we have a ton of earthquakes and high seismic activity. Places where we have upwelling mantle rock also include hot spots. And this is going to be Hawaii and Yellowstone. So this square box shows the upwelling hot mantle rock reaching the base of the lithosphere and sort of ballooning outward, kind of a mushroom cloud shape, and causing melting both within the mesosphere / mantle and within the lithospheric mantle, causing the production of large quantities of magma that feed volcanoes on the surface in the middle of your tectonic plates, usually far away from plate boundaries. So oceanic hotspots are a great example. Hawaii, as we talked about in the last lecture, is an oceanic hotspot, and we have the youngest volcanoes directly over the mantle plume on the island of Hawaii, and then we have older, less active, and extinct volcanoes as you move away from the hotspot. Because the Pacific plate has kept on moving, the mantle plume hotspot has stayed still, and these old volcanoes are now extinct and getting carried further and further away to the northwest from the current location of the mantle plume. I'm going to cover this, and then we will take a brief break in this lecture, and then we will talk about the relevant national parks. So this is the life of a hotspot volcanic island. At the very beginning, you end up with what's called a shield volcano on the ocean floor. These seafloor volcanoes have broad slopes, and they form these sizable underwater mountains. This one's called Luihi. It was recently renamed as Kamaehuakanaloa. So Luihi is an archaic name, and it is now officially Kamaehuakanaloa. So that's important to know. This is called, basically this is stage 1, stage 1A of your undersea volcano. It just slowly builds itself from lava flows that are pouring out on the seafloor. Eventually, Luihi Kamaehuakanaloa will reach the surface and do what's called the explosive pre-shield phase. So you have this volcano extending all the way upwards from the ocean floor, and when you reach the surface, you basically have no water pressure. So you end up with these huge explosions of lava and steam. During these eruptive phases, you get the construction of small islands, which will sometimes get blasted away by these huge steam explosions and then will reform later. This picture is a place called Surtsey, which is to the south of Iceland, and this is one of the rare occasions where we've actually witnessed this explosive pre-shield phase. It erupted in the 1960s and 70s, creating a series of volcanic islands in the middle of the Atlantic Ocean. Over time, Kamaehuakanaloa will reach the surface and will reach this explosive pre-shield stage, or phase. Once you get to the surface, then you are in the shield building phase, where you get these huge, very gentle sloped, very tall shield volcanoes. On the big island of Hawaii, this is Mauna Loa is the big one. It's the tallest mountain on Earth. It's over 33,000 feet tall because it extends up from the ocean floor. The base of Mauna Loa, the largest mountain on Hawaii, extends up from the Pacific Ocean floor, which is about 19,000 feet deep. So it's already 19,000 feet tall, but by the time it gets to the ocean surface. And then it's 13,000 feet above that to the summit of the mountain. And you can see in this three-dimensional map of Hawaii, it has very broad, very gentle sides. It is in the shield building phase. It is building up its large volcanic edifice. Mauna Kea, which is another volcano on the Big Island of Hawaii, you can see it's a little steeper and it's kind of pockmarked. Those are smaller volcanoes called cinder cones, which we'll talk about as this course goes on. It is in the post-shield phase. It is eroding faster than it is producing new magmas, new lava flows, and building up. So Mauna Kea is much older than Mauna Loa, and it is in its last phases of activity. Compared to other mountains, Mauna Kea or Mauna Loa, they're very similar in height, but Mauna Loa is the big one. From sea level, it's a modest mountain, about 13,700 feet. Mount Everest is 9 kilometers high. It is 29,000 feet. But then on Mars, we have another big, very large shield volcano that's actually the largest volcano in the solar system. It's 27 kilometers high from its base to its summit, and it has a broad caldera, or sunken feature at its surface that is 72 kilometers wide. It's roughly the whole volcano is roughly the size of the state of Arizona. So it's very large, and it is a shield volcano, just like these mafic lava flow constructed shield volcanoes on the island of Hawaii. We will take a brief break now and explore Haleakala and Hawaii Volcanoes National Park in the next part of this lecture.